Hello everyone, so today we're going to be working in the null space, specifically for a flow through a pipe described by pressure drop with a length and diameter in this. And additionally, we're going to be looking at density, viscosity, and velocity of the fluid. And we're going to be writing down the dimensional matrix of this. We're going to be demonstrating, explaining this null space that we're working in through this matrix, and then constrained by linear combinations of the null space. We're going to be putting some constraints around the null space that we get, which leads to dimensionless groups, specifically the difference in pressure over velocity squared times the density, length over diameter, and the Reynolds number. And we're going to do this through an automated system on Python. So to start off, to kind of get some groundwork where we're at. So first we have this pipe that we have by flow going through it. So there's 6 things that flow is affected by when flow goes through this pipe. So we have difference in pressure, which will be delta capital P. We have length, diameter, viscosity, the density, and the velocity. So what we can use here to be able to signify what these dimensionless groups are to form our dimensionless numbers that we want, we can use the Buckingham Pi method. So the Buckingham Pi, it basically equates all of these units down to 3 core units, which is meters, length, seconds, time, kilograms, mass. So we'll put these down here and make our little grid. We have delta P, length, diameter, viscosity, density, velocity. These just get a little more organized. So if you recall back to transport 1, we went over a little bit of the Buckingham Pi method, but not as in depth and not as an automated series. So to start off, we're just going to fill this in real quick and kind of see where we're at on that basis to kind of get a feel for our units. So to start off with delta P is our pressure. What's pressure? We're going to be measuring, let's say in pascals here. So pascals, actually newtons over a meter squared, or it's a force over an area essentially, right? So what is newtons? Newtons is kilograms times acceleration, or meter over second squared. So if we bring that back up into our pressure, our newtons, so we have kilograms times meter over meter squared per second, which simplifies down to kilograms over meters per second squared. So we have our 3 units right here. So we have meters, where we have kilograms to start, which is in the positive, so we just write 1. Our meters are in the denominator, so that's a -1. And then likewise with our seconds, that's -2. Our length is pretty easy, so we just have 1. And then since there's no seconds or kilograms in there, we just put 0. Diameter is the same way. Viscosity is a little tricky. If you remember back what viscosity is Pascal seconds. So we're going to take our units of pascals that we just got and then multiply it by seconds, which simplifies down to kilograms over meters per second. So we have our kilograms and then -1, -1. Density is how many kilograms per unit per volume, and those seconds, and then meters per second for our velocity. We have 0 kilograms. So that is what our Buckingham Pi method looks like right here, as we have our difference in pressure, length, diameter, viscosity, pressure, and velocity. So the goal of this is actually to get dimensionless numbers. So we have a Buckingham Pi method. I'm going to erase this real quick. So we want to get dimensionless numbers, and particularly these three. So we have three sets of zeros. Use a little 3x1 matrix. So the problem is, how do we get these, which is a very random assortment of numbers, into this? We can use a null space here. So a null space is essentially matrix multiplication using these unknown C values. However, the problem with this is that this is very hard to do by hand or on paper. Very hard to do. It's an infinite amount of values that exist within a certain subject. So the null space is very hard to do by hand, and there's an infinite amount of these C values. You may be asking yourself, why did I put these C1 through 6? Well, particularly, I did that because a null space is a dimensionless group, or a vector with 6 dimensions, not dimensionless group. It's a vector with 6 dimensions. So we can use matrix multiplication with these 6 vectors, and there's an infinite amount of these vectors, is what I meant to say. So this times our infinite amount of vectors, which has 6 dimensions, will give us our dimensionless numbers. So we have 3 equations that we're trying to get. So let's kind of try to figure out what we need to do, how many constraints we need to do to be able to make this achievable. So we have 3 equations. That is the goal. We have 6 unknowns. So we need 3 constraints total to be able to make this possible. We need to constrain 3 of these variables, that difference in pressure, length, diameter, viscosity, density, and velocity. So we can signify this by using these little pi ones, pi 1, pi 2, and pi 3. And these will signify our equations that we're using and where we're having our constraints at. Sit down. So first of all, we're going to constrain 3 variables here. So first, we're going to constrain our difference in pressure, our length, and our viscosity. So let's say for our first equation, we're going to have delta P is going to be 0 to the 0th power, so it's just going to be submitted to 1. We're going to have viscosity to 0, but then we're going to have that length to 1. We can't just eliminate all 3, so we can just pick that length will be 1. Likewise, diameter will be A. We'll have that density be B, raised to the B power, and that velocity will be raised to the C power. So for our next one, or pi 2, we will have this delta P will be 1, viscosity will be 0, and length will be 0. And then we'll have our diameter be D, D to the Dth power. We'll have our density be E, and then our velocity will be F. So for our last one, we'll have our delta P be 0, our viscosity be 1, our length be 0, raised to the 0th power, and then our diameter we raised to the G, our density, we raised to H, and our velocity raised to the I. So this is how our constraints look with our pi 1, pi 2, and pi 3. So now we're going to automate this on Python. Hello everyone, so today we're going to be working on the Python portion, I guess Google Colab portion, right? The null space and working with the null space to be able to do calculations based on certain restrictions and without restrictions as well. So I'm going to turn the camera a little bit just so, I don't know if it'll focus, hopefully it will. Okay, it's not really, but I have my previous Buckingham Pi method listed out right there. There it goes. So we have the kilograms, the meters, and the seconds, and then again with the six derivations that matter, or components that matter, I should say, is length, diameter, velocity, density, viscosity, and the difference in pressure. And then we have our null space of that C1 through 6. Those are our 6 different dimensions that our infinite vectors exist in, and our null space with 3 dimensionless numbers. So we're going to get into the Colab version of this just after that quick little reminder of what we're working on. So we'll start with importing the these commands so that we're able to run this. And now we're going to be making our Buckingham Pi array. So we'll put A is equal to np.array. We'll be doing right here. And then we're going to make our 3 like rows right now. So we'll start with the kilograms. So we have 0, 0 with a diameter, 0 with a velocity, pressure, or the density is 1, our viscosity is 1, and then our difference in pressure is also 1. So for our second one, we're going to be doing the meters now. So we have 1, 1, 1, negative 3, not 3m, negative 3, negative 1, negative 1, and that's it, I think. Yeah. And we have one more, which is our seconds or our time. We have 0, 0, negative 1. Oh, the last zero is not even. Negative 1, 0, negative 1, negative 2. So that is our first array. So we have our Buckingham Pi of that of our, again, this is our kilograms, this is our meters, this is our seconds. And then we'll just so we can organize this, with Buckingham Pi array. So for our next part, we're going to be importing this so that we can solve for these, actually using the null space itself to solve these through. I'll be using the equation nx. Actually, I'm going to be using the term nx is equal to sp. Then we'll use a linear algebra function. And then we'll be using the null space. So our linear algebra, the null space is a very common form from linear algebra, so it's very important for this. So we need to integrate that into what we're using today. And then again, as we all know, we're using the null space. So we'll put that A there. So now I'll show you like kind of what this array looks like that we got right here. So we're at nx. We'll just run this. There's what we got. So now we're going to be starting to generate our specific vectors. So if we remember back to what we were just looking at over here with that C1 value, that's what we're going to be solving for now. So we can start to generate these more and more and start to solve for them. That C1 is going to be equal to np dot linear algebra dot solve ns. I'm gonna put bracket 0, 4, 5. And actually, we're gonna put this. And then we want to get this we want to hit every single one of these. So we're going to put in this colon right here. So that we make sure 0, 4, 5 are always being hit. We're doing our next array. So we have the NP array 1, 0, 0, and then a dot. With the last apostrophe going on the end there. So this is our C1 value that we have here, and then we'll mark this up here with that C1 showing us our first variable is equal to these three sets of numbers. So again, what we did is that we set the first, which is 0 on coding, because it's like the first one it sees, and the fourth and the fifth, so our fifth and sixth more likely. And then we set those to 1, 0, 0 respectively. So our array that we got back was these with those constraints set. With this in mind, we're going to multiply our array to get our dimensionless numbers. So to multiply, we actually are going to be using this @ symbol. As the @ symbol is a little weird when you're doing vector multiplication, as that's what we're mainly doing. It's not straight multiplication, we're doing vector multiplication. So it's a little bit different. So if we want to run this like so, we will get these numbers. So these may look to be like, oh, that's a really small number. It's really just 0. So like this first one, again, we set these to 0. So we have 1, -1, 0, because that negative e to the negative 16th. Again, e to the negative 16th, e to the negative 16th, e to the negative 17th. So what is that? Well, it's really just length divided by our diameter. So we have our first dimensionless numbers. Now, it may seem kind of stupid at times, but for the harder stuff, it gets very interesting and very beneficial. So we'll write this down up here as our first dimensionless number. It's our length divided by our diameter. Because again, that's just 1 meter over 1 meter, or a meter over a meter, or some thing of length over another thing of length. So now we're going to do the other powers here. So we're going to be kind of doing it the same way. So we have our C1 vector. So we're going to be copying and pasting this because I'm lazy. Cool, we're good. And then we're going to be multiplying that. We're going to be changing what we have. So right now we have that length as 0. So we're going to be changing that to, let's do, what's it called? The viscosity as 1. Right? So we get our, we'll change that to C2. Nope. And then we'll run this. We get that array. Great. So nx at C2 is we get this number. So first, let's write this out a little bit. So we have our first one, our length is raised to the 0 to the negative. It's 0. length is non-existent. Our -1, so our diameter is to -1. Our what's it called? Our velocity is to the -1. Our density is to the -1. Our viscosity, running up viscosity, and then that's the first, and then our change in pressure is basically 0 again. So I'm gonna switch this over, and maybe can I make this bigger? No. So now we'll switch that. So our second pi 2, for our second dimensionless numbers, put that like that, is we have our density, our diameter, our velocity, and then our pressure all over viscosity, which, if we remember what Reynolds numbers is, we are literally just flipping that as this is our true Reynolds number. So if we were to flip that like so, I'll flip back over. If we were to flip that C2 as a -1, and then we run that, and then run this, same thing, but we get the positive ones, and then we get the -1, or that viscosity on the bottom. So let's run our final. Doing that. Let's get our final vector. So let's say we do our C2. Let's see, do I still have that copied? Yes. Let's get our C3. And then now, instead of that 1, we'll set this to 1. Oops. And then what's our C3? Get this array. Great. So we'll start up another code, nx at C3. Run that. So we get 0, 0, or here I'll write it out. So our length is 0, our diameter is 0, and then we have our velocity is -2. Velocity is -2. Our pressure, or our density, I think I said pressure earlier too, so sorry if I did that, I meant density. And then we have 0, and then we have our difference in pressure is 1. So what is that? That is for our pi 2. We have the velocity and density on the bottom. That velocity is squared, and then we have our delta P on top. So, in summary, we have exactly what we need right here with these arrays, and with all 3 of these with the velocity, the C2, and then the C1 with length over diameter. So thank you very much for joining me on this. See you next time.